Actually, I'm on that. I get the. Oh, you? I never got the grads. We not missed them. Not the grad school ones. The other ones.
Oh, the undergrad?
Undergrad ones. Yeah. Just emails from the president.
Oh, you get those.
Oh yeah.
Everybody does. No, there are other undergrads who aren't graduates.
Okay, we are shooting. Who's gonna be the director and getting club cut and so on.
Give me a
Alright.
dolly ear and a push-up.
Where's the thing?
Yeah, we need a dolly.
Dolly
Oh,
and
it's
push-up,
already
that's the
recording.
one that creates the
Huh?
background.
It's following your face? Oh, it is?
That's pretty cool. Oh, we need a soundtrack for this.
He's recording the sound, I believe.
Oh great.
I gotta get the costume.
I'll take Vin's smart ass remarks because they're safe or cost safe.
Yeah, forever. Don't show it to me, kids.
Prosperity for prosperity.
Okay, I apologize for being late today. I did not anticipate the early morning traffic. I haven't done this in a while, being this early, so we'll get better. And I will today send you an invitation link by email. You will click on it, sign up, and then we'll be all in a learning management system that we can use for our purposes. There will be more features than you need, but there is a discussion board and there is a place to upload files, PDFs, only tweets. You can make PDFs out of anything, and for the rest of it, there will be some of the places where you can do the stuff. Movies will actually post into the discussion, so as we go. Okay, so if you have actually gone over what we have done so far, you have basically all the rules of quantum mechanics all in one place. So maybe I should begin just kind of summarizing what they are. And as complicated and as weird at times quantum mechanics is, it's all about applying the same set of rules. No matter what system it is the same set of rules. So, what are those rules? We begin by choosing the system. And then, automatically, by choosing the system, if you decide to use quantum mechanics, whether you like it or not, this immediately associates a Hilbert space of states. And then everything you need to know or want to know is described by vectors psi, which are the element of the Hilbert space of states. So anything that system can do is described by some vector in a Hilbert space of states. Now, when you have chosen the system, you will typically know some variables. We don't go and invent a system out of the blue. We usually know something about classical physics of that system. And so the variables could be position, momentum, energy, spin, angular momentum, whatever. Any collection of variables. And these variables are promoted to operators. On the Hilbert space of states. Now, classical physics would tell you that there will be some relationship between these variables. So for example, if I use the free particle, so let me not go that this. So if I say that my system is free particle, of mass m, say moving along a straight line, then I know that I have variables which are position and momentum. And in classical physics, these two are related by Poisson bracket, like this. So there is a Hilbert space of states, which perhaps still needs to be constructed in more detail or specified in more detail than we have done for this particular system so far. But we know immediately that these two variables become position and momentum operators respectively. And we specify at this point a representation What it means is that if I take the position operator acting on some vector in a Hilbert space, then I will simply stipulate that the rule of how this operator acts is by multiplication. So this will be coordinate representation. For example, so in the coordinate representation, position operator, when it acts on a vector in a Hilbert space of states, will simply multiply that vector by the value of the coordinate. And momentum, when it acts on that state, will act as minus IH bar times the derivative of that state. We can have alternative representations, momentum representation, in a momentum representation, x and p are still operators, but we will stipulate that x acting on a state which now is a function of momentum will be I h bar d psi dp, and momentum itself acting on that state is simply multiplication. Whether you choose this or this representation or some alternative, it really doesn't matter. The two representations are connected anyway. We will see how in a minute. But we have to choose one.
Can we choose representations based on these other variables?
We
like
could.
Energy with that?
We could.
Okay.
Whatever is appropriate. Classical physics should tell you what's appropriate. It depends. For example, if I'm describing free particle of mass m, then relevant variables are xp and energy. If I'm describing the free particle with a spin, then I will include the spin variables and I will have additional labels. Once we choose the representation, we actually have a translation of this into quantum mechanics, which is concrete. And strictly speaking, you can think of this being realized by quantum mechanical substitution, where x goes to x, p goes to minus I h bar times per. Okay. Now, states have to have some properties. We would normally like states, if possible, to be normalized to 1. I will from now on use either Dirac's bracket notation or my old-fashioned parenthesis notation for scalar product. This is the same as psi. It really doesn't matter. What it basically means is that if I'm using coordinate representation, then in a coordinate representation, the integral should be 1. Technically, it should be less than infinity, but if it's a finite number, we can always normalize it to 1. You will see why we use the normalization to 1. Okay. The question becomes, how do we construct these wave functions? And that itself is not always necessarily trivial. And perhaps a little bit of a history is in order here, how the construction came about. And so we'll write down this to understand how and the why. Some history is needed. So at the end of the, I shouldn't say the last century before the last, so the 21st, right? So 19th century. It's kind of funny. Because all my life I've been used to say, you know, at the end of the last century, the 20th century. There were several peculiar facts that people learned about. One of the first one, and many of these happen to have been discovered people who were not necessarily physicists, was that certain kind of lamps, they were basically low pressure lamps. Basically they were pieces of glass which contained 2 electrodes and a gas under a low pressure, let's say neon gas or something. When you look at them through the prism, you see that they emit light, but they don't emit a continuum of wavelengths. So if I have here the wavelengths of light, they are like these fluorescent ones. In fact, these fluorescent ones are low pressure lamps, and literally it looks like a tube. You have one electrode here, another electrode here, you have gas inside, You can use air, but air is a mixture of gases, it's a bit more complex. And this emits light, and these fluorescents actually emit continuum light, and even if they don't have this coating, they will emit bluish light, but not others. So you need to carefully look at actually what they emit under the prism, and you would see that you don't get all the wavelengths, but you just get some specific ones. So there is a discrete spectrum. Also, if you shine the certain wavelengths, or if you shine the light through such a system, you would actually notice that it only absorbs certain wavelengths. And that, if you think about classical physics, is in contradiction with what we know about electrical charges. Electrical charges presumably are someplace inside of the atoms, and they experience the force. We know that atoms exist, that atoms are stable, and so most natural force that you can assume that acts between the charges inside of the atom is Coulomb force. There may be other more complicated pieces, but that's a primary effect. And if the atom is stable, one way you can think about it, why it's possibly stable, is because something like an electron inside of the atom behaves like a planet orbiting the sun. It doesn't fall into the sun because of inertia, right? It has a velocity which is tangential to the orbit around the sun, which keeps it basically by inertial effects in that orbit. Now, it turns out that that's a problematic because electrical charges which experience acceleration, and these charges do experience acceleration, happens to be the centripetal acceleration, right, caused by the Coulomb force, will actually emit energy. They will radiate electromagnetic waves. That was what Maxwell discovered. And the spectrum of that radiation should be continuous. Instead of seeing just some specific wavelengths, you should see all wavelengths. So that seems to contradict what we know about classical physics. So this somehow didn't work. The first proposal on how to resolve that was Bohr's model of an atom. And we'll briefly go about it. It's not very complicated. It's very simple. It's wrong, but it gives a good quantitative picture, at least the spectral lines. A second problem that was quite interesting and became an issue at the end of the 19th century was the problem of describing the emission or absorption of electromagnetic radiation from the so-called black body. Black body is basically nothing more but a system in which you have electromagnetic radiation in equilibrium with the matter. So you have basically a furnace of some sort with a little hole in it, and that furnace is at a particular temperature, and through the hole electromagnetic radiation is emitted. And the question is, what is the spectrum of that electromagnetic radiation? And classical physics simply cannot give you the correct picture. Luckily, measurements were done, and so the experimental curve which describes actually energy density or intensity of the radiation was known and has a peculiar form. So this is intensity versus the wavelengths.